Okay, and so we also covered this second order optimization briefly, right? So let's see. So last time we didn't discuss in detail about the fully the GoogleNet and the ResNet and so on, right? So let me just briefly go over with them. So in the case of GoogleNet, there is one default module that is repetitively used in this whole network architecture called Inception Module, right? I don't know why it is called the Inception Module, but yeah, in this case, we can now extend our notion of the particular layer, whether it is a fully connected layer or convolutional layer or maybe recurrent layers and so on. And now we can think of some hybrid layer where one module or one unit of the layer is composed of multiple different types of layers. So in this particular case, it has a 1x1 convolution layer and also some pooling layer, and also basically it has these 4 different branches, right? And then they are merged together at the end, right? And so this entire network architecture works as a one unit or one common module that is repetitively used when stacking our deep neural networks, right? Okay, and there is a different versions of the Inception modules. So this one is the first version, and this one is not being used in these days. And so but at least using this simpler or more ancient architectures, we should be able to understand how it works, and also in terms and have an understanding about this activation map size. Okay, so it has the spatial resolution of width and height and depth in this number, right? And then first of all, you have to understand this 1x1 convolution, and it usually works as kind of dimension reduction. So when talking about the 1x1 convolution, it's not related to convolutional neural net directly, but it's more of a fully connected layer. So let me explain it briefly. So suppose we have 3x3 and the depth as maybe 128, okay? And then if we do the 1x1 conv, and then our filter size will have the spatial resolution or size as a 1x1, but because of the fact that we need to, we should make the depth of our filter to be the same as the input activation map's depth. Our filter size should have the depth as 128, right? So if this filter is applied at the very left and upper position, and then it will produce one single activation output, as a scalar value, right? And then altogether, this filter is applied at this position and this position and so on, right? And so using this one filter, we will have this 3x3 activation map of the depth of 1, right? For 1x1 filter, right? And then if we have maybe 10 different filters having this 1x1 size, and then we will now have yeah, 10 different depths or activation maps, right, that are concatenated depth-wise, which results in this 3 by 3 and by 10 size of an activation map as our output, right? So first of all, this kind of 1 by 1 filter doesn't consider the neighborhood or adjacent information in a spatial dimension. So if we compute the activation map at this position, and then it doesn't look at these neighboring pixels, right? So it doesn't try to capture any kind of spatial patterns like, so if our filter was like this kind of shape, and then we know that this is trying to capture this kind of pattern or this kind of edge, right? And then that activation, and then that activation map, that activation value is corresponding to this center pixel, right? So from the perspective of this center pixel, this convolution is usually taking into account the neighboring information spatially, right? But in the case of 1x1 conv, we don't actually look at the neighboring pixels. So that way, it doesn't try to capture spatial kind of patterns, but it actually combines the information within this particular position, but it actually combines the information distributed across this dimensional or depth-wise information, right? Okay, so if the first steps was trying to capture, the first steps was corresponding to the strengths of maybe cat's nose, okay, and then this is maybe cat's eye, and then for this 1x1 conv, and then the first and the second value was maybe 3 and 5, which are all positive values, and then we actually try to capture the information, which is a high when both of these cat's eye and cat's nose are shown simultaneously within the same position. Okay, so that way we can actually combine these information within the same location, but across different depth-wise information. Okay, so we differently combine these information to create one particular activation. Okay, and then we will have another filter, and it doesn't look at any kind of information about cat's maybe nose or ears, and then the activation, the filter coefficient will be set as 0 for the corresponding dimensions, and then it will try to involve some other information available in the other channels, okay, in the input activation map. Okay, and also this is actually viewed as this one is actually viewed as a simple, fully connected layer. Okay, so if we have input vector in a 128 dimensional space, and then it is just like 128 dimensional vector as an input, and then we are producing like 10 dimensional output, right? And then what is our input? Our input is each of our particular spatial kind of positional vectors, those kind of vectors. So these vectors are sometimes called a fiber, so fiber means do you know optical fiber? What's the meaning of an optical fiber? So it's like 광섬유 알아요? 광섬유 이렇게 광통신하고 뭐 이러잖아요. 그래서 이제 한 이 튜브 안에 이제 광섬유들이 막 이렇게 여러 가닥들이 있잖아요. 그래서 요 하나하나의 요 이제 가닥들 하나하나를 우리가 이제 파이버라고도 이제 불러요. Okay, so we pick up each of these fibers, which is all 128 dimensional vectors, and then we take it as an input to this fully connected layer, and then we will get the 10 dimensional vectors, and then we rearrange this shorter length to fiber, which is now in the 10 dimensional vector, in the same spatial kind of layout of 3x3, right? So we can think of this 1x1 conv as this fully connected layer. And usually this 1x1 conv is used to reduce the dimensionality. So for example, if we look at this, let's see. Like this kind of structure, and then if we have a 128 dimensional kind of activation map, I mean channel size of our activation map. And then suppose we want to apply 3x3 conv given this activation map. And then this 3x3 filter size, input should have maybe more spatial length, I mean spatial size, so that the 3x3 conv makes sense. But anyways, 3x3 convolution has to have the depths as the same as the input activation map as 128, right? So there is no option other than that, right? So in this case, the filter size, even though the spatial resolution is only 3x3, which is really small, but our channel depths should be quite large, following the input or matching the input activation map steps, right? So as a kind of pre-processing step, by just adding or applying the 1x1 conv, and then suppose we just change it by this 1x1 conv using maybe 10 filters, and then our activation map would have the depths of only 10, right? So in this case, if we apply the 3x3 conv, and then now we can have the filter size as the one that has the depth of 10, right? So so that way, we can reduce the number of required parameters to apply the same size of, same spatial size of a conv filters, okay? And also sometimes it is also used in this manner, which is called the bottleneck layer. So if you understood this VGGN as receptive field examples, and then suppose we have a activation map with the channel size of C, and then we want to apply 3x3 conv layer, and then we want to also obtain the output activation map having the depth of 3. And then in this case, by just assuming just one single layer, and then we know that this times this is the total number of required parameters in our convolution filters, right? So in this case, we can imagine or we can draw our convolutional layer in terms of an input and activation maps depths or channel as this form, C and C, okay? And then here, if we apply the 1x1 conv as a dimension reduction kind of module, and then it is only showing the depths, right? So we are not drawing explicitly the spatial resolutions in this case. And then suppose we just reduce the depths, for example, as 128 as maybe 10, okay? And then using this much reduced kind of depths of our input activation map, and then what will be our parameters of conv layer to obtain the same channel of an output as C, and in this case 3x3 by 10 times C, right? So this input depths is now changed into 10, right? So it is one possibility, but usually people how the people designs this so-called bottleneck layer is as follows. So in this case, like this. So given the input activation map with the depth of 10, and then we generate the output activation map that has the same depths as the input activation map. So in this case, 3x3 by 10 and 10 will be the number of parameters for this 3x3 conv layer, right? And then now we apply another 1x1 conv in this dashed part, right? So now we actually, rather than reducing the dimensionality or reducing the channel, we actually increase the channel from 10 to C. Okay, so in this case, it is also designed as 1x1 conv. Okay, so that way it has this bow tie kind of structure, or this is called the bottleneck kind of a layer or bottleneck kind of a structure. Okay, so we actually reduce the dimensionality and then do something that we actually want to apply onto the into the input information, and then we reconstruct it back to the original kind of dimensions. So in this case, it is composed of 3 layers, right? So this part is a 1x1 conv, right? So in this case, what would be the parameter size? The number of total parameters. It is simply 128 times 10. Although we just ignore the bias in this example, right? Okay. And also from the perspective of a 1x1 conv, and then what is the filter size of this? What is the filter size of one single convolutional filter in this 1x1 conv? It is just the same as the channel, input activation channel, because the spatial resolution is just 1x1, right? And then this one is the number of parameters required for one channel, and then now we need 10 different channels where 10 is the output channel. So our parameter will be just 128 by 10. Okay, so this is the total number of 1x1 conv filter parameter, or 1x1 conv layer parameter. So in this case, this is our total length, total number of parameters for this bottleneck layers. Okay, so overall, this one could be much smaller. Oftentimes, this the sum of these 3 numbers is usually smaller than the number of this a single conv layer. Okay. So, any questions about it? So in GoogleNet's Inception, maybe V3, I think it's V3, version 3. But so in this case, before applying this 3x3 or 5x5 conv, which has a relatively larger spatial size, and then in order to achieve the computational efficiency, we first apply 1x1 kind of dimension reduction or 1x1 conv. Okay, so that we can reduce the input activation channels. Okay. Okay, so in this case, so we separately also apply 1x1 conv, and then using this, the padding with an appropriate size. So in this case, we add padding size as 1, and then here we add the padding size as 2, and then we can maintain the same spatial resolutions from the input, between the input and output, right? And then given the output activation map from each of these 1x1, 3x3, and 5x5 conv, and then we just concatenate those output activation maps in a depth-wise manner, right? So now you guys can understand these numbers, right? So we have 28 by 28. This is a Inception module version 1, but it has a depth of 256, and then we apply 1x1 conv, and the number of convolution filter is 128, and then 28 by 28 by 128, and then in this case we apply 192 number of convolution filter whose spatial size is 3 by 3, and then using the padding size as 1, and then we obtain this number of output activation map. And then when combining these two, we just concatenate them in a depth-wise manner. So using the same spatial resolution, with the same spatial size, and then the depth is added together, right? Okay, and then here, at first when I studied this Inception module, I came up with the question about this part, 3 by 3 pooling, which is our kind of max pooling module. So in this case, how come do we achieve the same spatial resolutions as 28 by 28? So here max pooling is applied channel wise, so it doesn't change the channel size, right? So we have the same channel size, but how can we obtain the same spatial resolutions when applying or after applying the pooling or max pooling? Can anyone explain how we can achieve this the same spatial size? So again, the question is, heading? Okay. So let's think of this max pooling in terms of its, of course, the filter size and also padding and also stride size. Okay, stride size. So when applying, for example, 2 by 2 padding, and then we typically use the stride size as 2, right? So if we have this 4 by 4 activation map, and then if we apply 2 by 2 max pooling, and then we apply the max pooling over here, and then obtain one activation output or scalar output, and then what will be the second one? The second one is applied at this position, right? So in this case, the stride size is actually 2. So when applying the max pooling, we usually use the filter size to be the same as the stride size when applying the max pooling, right? But this max pooling can just be viewed as kind of convolution. So in the case of convolution, we actually combine those numbers captured within one single filter or one single window. We just combine them linearly, right? But we just apply the max operation. Okay, so that is the main difference of this max pooling from the convolution, right? So instead of doing the linear combination, we apply or we pick up the maximum value. Okay, so that's the only difference. But from the perspective that those filters are moving around and then give us each different outputs from applying each windows at different positions. In that sense, the convolution and max pooling is essentially the same, right? So in this case, if we apply 3 by 3 pooling, and then we can just set our stride size as 1, and also the padding size as also 1. Okay, in that case, we can easily understand that it will give us the same spatial size.
If you use a stride of 1, then what is the point?
The point is we are actually propagating the max values to neighboring regions.
I can see what is happening, but I don't know.
Yeah.
Why that would be a good idea.
Okay, so okay, so in this case, let's just apply the simple case of 2 by 2 max pooling with the stride size as 1. So in this case, what will be the maximum value? I mean, let's just set the padding size as 0. Okay. So in this case, it will not give us the same spatial size, which is different from applying 3 by 3 max pooling with the padding size as 1. So we are considering a different case, but I'm trying to explain the effect of max pooling with the overlapping kind of windows, or the stride size as smaller than the filter size. So in this case, the max is 2, right? And then if we apply the max pooling over here, and then what is that? The activation map will be 8, right? And then moving it to the right, and then the activation would also be 8, right? So if we imagine it, and then 8 will be propagated in this manner, right? So the single strong kind of signal or strong activation value is propagated to the neighborhood region, right? So if that activation value was was indicating the strength of observing maybe cat's nose, and then cat's nose was found really strongly at this particular position, but when applying the max pooling with the overlapping windows or stride size smaller than the filter size, and then we are just propagating or duplicating this value or this value to neighborhood region, so that, okay, so even though the cat's nose were found strongly at this particular position, but at in the next layer, we are just giving, or we are just changing this input activation map in a way that, okay, that strength was found also in these neighboring regions. Okay, so that's the intent of applying max pooling with the overlapping windows. Does it make sense? Yeah, or what's that?
I don't think there will be a strong foundation for this and actually work.
Yeah, but essentially max pooling is actually intentionally losing some information, right? So for example, if we apply the max pooling over here with just the typical setting with non-overlapping windows. So for example, the activation map will be also 2 and 8. And the spatial resolution for the horizontal or width will be reduced from 4 by 2, right? But we typically think of this 8 is actually the representative of this part, right? This part. So when, I mean, from the later layers, it is viewing our image, or it is viewing our input as having 8 at all the different, I mean, at every different positions. I mean, so it will be kind of equivalent to like having 2, 2, 2, 2 and 8, 8, 8 and 8 in a full resolution. Okay. So when converting this information into the full resolution of our image, and then the later layers will view or will consider our input is looking like this. Although, it is not a rigorous kind of explanation, but max pooling is essentially the step of losing the information intentionally, right? So that we don't tell, or we don't actually ignore where this 8 came from among 4 different possible positions, right? So that way, our neural net is having the flexibility of like slight deformation of some kind of shape, right?
So does it help in making the model less prone to overfitting?
Yeah, kind of, yeah.
But am I right to say that if let's say the image that we are working with has very little pixels, then we probably shouldn't be doing this?
What's that?
If the image that we are working with have very little pixels, then we shouldn't be doing this. Should we do max pooling with if the dimensions are actually very small. So maybe like in your example, it's 4 by 4 pixels, right?
So
then probably it doesn't make sense to do max pooling.
Right. Yeah. So if our original input image is maybe 16 by 16, and then we cannot apply more than 4 times of a max pooling with the window size is 2 by 2, right? Because it will go into like a sub-pixel level. I mean, we need the pixel actually smaller than our original single pixel, right? So in that case, we have no other options applying more max pooling. So in general, it would be great if we give a higher resolution of an input, and then it's generally the performance or accuracy will become higher. Yep. Yeah. But typically, if you just if you build your own model, and then it will take the same size of an input. So you just have to fix your input image size as maybe 128 by 128 or 64 by 64 or even maybe 32 by 32. So it's your choice. I mean, it's not directly. I mean, it's not related to the data set size, because you can always resize your input images, right? So once you have a smaller size of an input image for your model, and then it will be trained much faster, but you expect a little bit less accuracy than the model taking a larger input image size. Okay. But if you're interested, and also if you're interested, and then you can just look for this. So FCN. So this acronym is for not fully connected network, but it's actually fully convolutional network. Okay. So fully convolutional network. So in this case, it can actually handle a variable size of an input image size. So in this case, by applying something called the global pooling or global average pooling, we can always this kind of network architecture can actually have an ability to take the variable sized input images. So it is it is quite often used in object detection or segmentation, and those kind of a little bit specific computer vision tasks. So we might have a chance to discuss about it, but any other questions? Okay, so you now understand how this pooling layer is mixed together with the other conv layers while it maintains the spatial resolutions. Okay, and let me briefly mention about how come we found this particular architecture, or so it was invented by Google, and this Inception module was invented in the following manner. So we basically want to define our unit that is composed of multiple different branches, and at each branch it applies different types of neural nets, like max pooling and maybe 1 by 1 conv, and then maybe 3 by 3 or 5 by 5 conv, and so on, right? So once we have this kind of flexibility to define one particular unit in our neural nets, and then there are so many different possibilities, right? And so what Google did was, this is also called sometimes it is called the auto ML, or kind of automatic machine learning, or it is called the architecture search. Okay, so this architecture search, the main job of it is to find the optimal particular architecture that will work best for our own task. Okay, so here the particular task of our goal is just the ImageNet classification. Okay, and then Google actually applied all the different types of variations to define one particular module, and then they just stacked that particular module over and over. So that's how they constructed this GoogleNet. Okay, and so the key part is to find optimal architecture that will form our, one unit of our layer, right? So so there are many different optimization algorithms. So how we design this particular module is actually not trivial, and that is not done by our gradient descent, right? So our gradient descent will require a fixed neural net architectures, right? So before applying or before running our gradient descent modules, we actually have to define, prior to running this gradient descent. So designing or determining the optimal architecture is actually our role, right? So it means human has to take care of that part, right? So that way, that kind of manual part or kind of human side of tasks, we want to automate them. We want to even automate that part, which is still left at the human side by doing the manual kind of search or manual kind of repetitive like trial and errors, right? So that way, this auto ML isn't kind of an effort or the research areas to kind of automate the human side of the tasks when doing the machine learning, which is beyond this gradient automatic gradient descent optimization. Okay, and one example is to optimize our hyperparameter, such as a learning rate, and also another hyperparameter is just to design our particular module that will work optimally for our own task. But this optimization, this finding out the optimal design of our neural net is a lot more challenging than just finding out the optimal learning rate, because that is, that falls into the category of categorical or combinatorial optimization problem, right? So if we found the particular learning rate is too high, and then we have a notion or sense of like how to change this parameter. If it was too high, or if the objective function blows up, and then we now have the idea, at least we need to reduce this parameter to a smaller value, right? But in this architecture, if this architecture is not optimal, and then where to change, and into what kind of modules, right? So in that case, it is a really combinatorial. We have to do a lot of trial and error by mixing and matching a lot of different modules, right, with the different orders and so on, right? So there are, this is called the combinatorial optimization problem. By searching through many different combinations of possible choices, and then we want to find the optimal solution, right? So there are not many kind of combinatorial optimization techniques that works pretty well, but there are a certain method, and one of them is also one of them is called. Have you heard about this genetic algorithm? So there are several different algorithms that can be applied to the combinatorial optimization problems, and then Google did a lot of work, or basically running their powerful machines to run this combinatorial optimization algorithms to find out what is the best modules definition, or this kind of particular structure. And this is one architecture found by Google at that in that era, or in 2014, right? And then Google continues to this kind of research, and also it has to run or perform really large number of this trial and error kind of thing by changing this module. What if we change it into 7x7, and then what if we just apply this max pooling over here? So sequentially or in parallel, there are so many choices. So yeah, so Google actually found one particular optimal kind of module through some combinatorial optimization algorithm, but there is no magic there, and so it has to run really many different architectures and then find out the best one, and so it requires a lot of computational kind of machines, or so Google or Facebook and those really large companies are just doing the research in this field, but not many from the universities or kind of individual basis. But anyways, they continue to do some search, and so they apply some interesting algorithms from reinforcement learning and maybe some other algorithms to find out the optimal architectures. And so if you are interested, and then you can also do your own project in that direction. Okay. Any questions? So let me. So I believe I covered this Inception module. So if you still have a question, please let me know. And this is a batch normalization. I mean, the main goal of this batch normalization is to provide the proper range to the nonlinear units so that the gradient doesn't get killed, right? Or the input activation or output activation values are not saturated or remain just as 0. And so it is mainly used just before the nonlinear activation units. So once, if we use it just before convolutional layer, and then even if we change, or basically batch normalization is scaling and shifting our activation values, right? And shifting means we add some bias or some value, and the scaling is just multiplying particular value to our input activation value, right? And so in that case, the convolution is just nothing but a linear combination, right, of the input. So our convolution parameters plays a role of scaling and shifting in their own manner given the input activation maps, right? So batch normalization doesn't need much before the conv layer. So did it answer this question? If you guys have more questions about it, let me know. Okay. Okay, and also let me briefly explain these modules. Okay, so basically you understood the basic intent or the role of this module, right? So even though our GoogleNet is composed of many Inception modules, 10s or 20s and so on, but after maybe 4 to 5 Inception module layers, and then we just directly pass it through their own fully connected layers. Okay, and then we get the output in terms of our 1,000-dimensional softmax vector to just compute their loss with respect to the ground truth probability. Okay, so in this case, even though this whole network is our main goal that we eventually want to obtain, but stacking these layers more and more, we make our training more difficult, right? So in the ancient age or in the older ages, if you watch it, this RNN's like lecture videos, And then you probably remembered that when Justin recapped this part, and then Justin mentioned that this kind of network training scheme is used before the invention of this batch normalization, right? So if we didn't have a batch normalization, and then when stacking these layers, and then it will easily make our network not being trained at all, right? Due to this gradient vanishing or improper ranges given to the nonlinear activation units at some point, right? So it will make our training process really difficult, right? So in the previous errors, we actually used this kind of strategy. So even if we want to obtain, we want to train or maybe 20 layers, we just first train only 4 or 5 layers first, and so it doesn't exist at all at first, and then we only train this part by using or by applying the loss at this particular layer. Okay, and then now this part will get trained to produce kind of suitable to extract some suitable patterns, right? And then now, we kind of make or we make this lower layers stable at first, right? And then we stack more layers, and then apply this part, okay? And then this part will get also trained, and also this part will get also like fine-tuned, right? So fine-tuning means, so this part was once trained by using this shallower version of our network, and then we throw this part away, and then instead we stack more layers that we want to add, and then we have this part, right? And then we now apply this loss function at this point, and then this part is starting with the random initialization, right? And this part will start with the previously trained parameters that were once optimal for this shallow version of our network, right? And then we either not train this part at all, or we apply the learning rate as really, really small value, as maybe 0.01. And then for this part, because it starts with the random initialization, it has a long way to go to converge as their optimal values. So in this case, the learning rate could be 0.01, which is much larger than this value. So that's that was kind of how we kind of stack, or how we train this deep neural net architectures, like one by one, or kind of lower layers first, and then stack more layers, and then train that part, and then once they become stable, and then we stack more layers. So that's how we train this model. Okay, but nowadays we don't use that strategy at all, right? Because we have a really powerful tool of a batch normalization. But when they are working on this Google Net, it is how the entire neural net is trained. Any questions? And also, alternatively, we can actually utilize, we can actually train this model simultaneously. I mean that, okay. So we have 3 outputs, right? And then it will give a 1,000 dimensional softmax vector, and also we have 2 different versions of 1,000 dimensional vectors, and then we apply the same 1-hop vector, which is our ground truth, at this position and this position and this position, right? And then we can actually train this network by using this 3 different points of our neural net outputs all simultaneously. So in that case, so this one is giving us like cross entropy loss, and this one is also giving their own cross entropy loss, right? And then our objective function should be scalar. So if we consider different losses at different positions, and then they should be added together at some point. So our loss function should be something like this, okay, which is a linear combinations of the different losses that we consider. So that way we just produce one single scalar output, right? So in this case, this alpha, beta, and gamma is our hyperparameters. So in this case, we can maybe design this alpha, beta, gamma, and their sum as 1, okay? So without kind of losing any kind of generalization. So it is just the equivalent. I mean, because it, like, applying this, and then maybe applying this will produce the same output, because it's just a matter of scalar multiples in terms of our loss function value. Yeah, it doesn't affect the optimal parameter value, right? It doesn't change that. Okay, so in this case, if we just apply like 0.98 and 0.1, or 0.01 and 0.01, and then it is giving much higher weights to this part, right? And then if we have maybe 2 and 3 and 5, and then we are giving more weights on the last part, right? Okay, so if we're gonna train this model by using these 3 different loss values simultaneously, and then you can actually change these parameters during the training time. Okay, so that way, in the first stages of a gradient descent, and then you apply this kind of weights, because it will be difficult to train using the third loss, which is the output after stacking a lot of layers. I mean, that will be really difficult anyways in the first stages of the gradient descent, right? And then you just gradually decrease these values and increase these values, and then during the single set of the gradient descent iterations, you can actually change these hyperparameters in a way that these values become larger and larger, and this becomes smaller and smaller, right? So that is also another kind of strategy by using all the losses, produced at different positions. But whether you just exclude it, we just ignore this part, and then you just train this part first, and then once they are stable, and then you just stack the second part. I mean, that is the first strategy that I explained, right? So in this simultaneous version and the sequential kind of stacking version, there are 2 different strategies available. But both of these cases, once you finish your training, okay? Once you finish the training, and then this whole part is gone, okay? We don't actually use them at all at the test time, because we actually want to use the output, at the really deep neural net that we intended. I mean, with the large number of depths that we originally intended. Any questions? So, in this case, we now involve our loss function. I mean, our loss function is involving multiple different terms, right? So even though they are all the same kind of cross entropy term by applying the same ground truth labels, but they are actually using a different outputs, right, at the different layers, right? So technically these 3 terms, 1, 2, and 3, are different loss terms, and then we linearly combine them, and then in general it is called the multitask learning. Okay, so this is called the multitask learning. So why is it called the multitask learning? Yeah. So in this case, let's look at this lower layers or lower level of our network. So that lower layers should be utilized in order to minimize this part, and also in order, it should be minimized. It should minimize this part and also this part, right? So at this position, I mean, the output at that level, should satisfy multiple different criteria or objective functions, right? So that way, the task that this layer output should achieve or should take care of is actually composed of different tasks, right? So that's how we call it as a multitask learning. Okay. So this kind of multitask learning, I mean, one simplistic example will be like regularized version. Okay. So if we make a linear regression or logistic regression with the L2 or L1 regularization, and then we can actually draw our computational graphs like, let me add one more explanation about this. So in this case, our loss function should arrive at the single node, right? Because our loss function is always scalar value, right? So in this case, if we just finish or complete our computational graph by using, for example, this kind of hyperparameters, and then it will be like this times maybe 0.2, and this times, I mean, we will have the node that will compute the cross entropy loss, and then it is multiplied by, it gets a little messy, but and then it will be multiplied by 0.5, right? And then they are added together. So this is our full computational graph, right? And then the loss is computed at this point, and then it will be backpropagated through this multiple branches, right? And so if you imagine this regularized version of a linear regression or logistic regression using L1 or L2 regularization, and then we will have our data. I mean, this is really conceptual figure, but this is our parameters, right? And then we have our data fitting loss, which could be cross entropy or L2, I mean the least, I mean squared loss in terms of linear regression, okay? And also these parameters are also branched out into L2 regularization paths, okay? And then using some regularization parameter that is assigned to this regularization term, and then we will have this final node in our computational graph, right? So in this case, from the perspective of our parameters, that should minimize the loss incurred by this position, and also the loss incurred by that branch or that kind of different kind of roots in our computational graphs, right? So in that sense, our parameter should satisfy two different criteria. So that way we call it, we can call it as a multitask learning, okay? And also another multitask learning example will be, have you learned about the autoencoder? Autoencoder? Does anyone know autoencoder? Autoencoder. Okay, anyone not knowing the autoencoder? Doesn't know autoencoder at all. Okay. Okay, so yeah. So autoencoder is something like this. So suppose we have some facial images. So we collect the facial image of each person in this room. Okay, and then suppose we want to build up our classifier of determining the gender of a person, whether he or she is a male or female. Okay, and then our gradient, suppose we just built up our convolutional neural net, and then at some point it will be composed of a fully connected layer, right, which has the spatial resolution of 1 by 1, and then after then we will obtain one single scalar which will pass through the sigmoid layer. Okay, and then if it is a 1, close to 1, and then it means a woman, and if it is a 0, and then it means it is just a man, right? So that way we can build up our kind of binary classifier, right? So in this case, we can actually design this multitasking learning by incorporating something called the autoencoder, and autoencoder works as follows. So suppose at some point during our convolution layer, it is having maybe suppose it is 4 by 4 by 3, right? 3 is RGB channels, and then the spatial resolution is at some point reduced by 2 by 2 and 128, for example. And then now using this activation, we will just pass it through the rest of our neural nets so that it produce one single scalar output indicating male or female, but also this output is actually going through the another branches of our neural nets. Okay, and then by just carefully setting up our parameters in our convolutional neural nets, we can actually increase the spatial resolutions as 4 by 4, and then also suppose at the last convolution layer. So in this part, it's a really sketchy figure. So suppose at this point, so this is a conv layer that has the filter size as the number of filter as 3. So in this case, we have a 4 by 4 by 3. Then we of course have the input images that will fill out particular values in each of these elements in our tensor or 4 by 4 by 3 activation map, which is our input image. And then this guy, we intentionally obtained the same size of an output activation map as the input activation map. And then we just apply the L1 or L2 loss element wise in this manner. Okay. So in that case, so this pixel, so this RGB, and suppose this was 111, for example. Suppose the pixel values at that position was 111, and then after going through some conv, and then at this point it is branching out into 2, and the lower branches is transformed into 4 by 4 by 3, which is the same size of an activation map as the input. And then suppose this value was maybe 83. So in this case, we can actually generate the loss as the difference between these two, which is 111 minus 83. Okay, and then in this input activation map, we have 4 by 4 by 3, 48 different pixels, right, in our input activation map, and we also have the same number of output elements in output activation map, right? And then we just compare this element-wise, these values element-wise, and then we just sum them up. And then we can think of this L1 loss generated by each pixel in our output activation map, right? So in this case, we have the L1 loss, as the summation of all the loss generated by the element-wise manner by just comparing input and output activation map. So let's call that term as the second term, and then so here we have our original task and its loss function, which is defined as binary cross entropy, right? So if that person was like female, okay, and then it is it has the label as 1, okay. So if it is a person, this person is a male, and then it will have the label as 0, and that way we can just consider the binary cross entropy in this manner, right? So in this case, we can apply the same kind of strategy of satisfying both of these criteria, like 1 and 2, and then we can consider their hyperparameters, which is like weight values assigned to each of these loss terms, right? So if we imagine this L2 or L1 regularization, and then our task is fixed, right? So so in this upper figure, so even though our training objective function involves or include that L2 regularization term or maybe L1 regularization term, our main goal is to maximize the performance of that data fitting on the test data or unseen data, right? So in that case, this L2 regularization term is actually kind of an obstacle that actually prevents us from maximally fitting our training data, right? So that way, the bottom part or that L2 regularization works as regularization, right? So the main idea is not to maximally fit our training data, right? How do we do so? We actually have an additional loss term in our loss function, and that way we have to minimize the lower part as well as the upper part. So that way we kind of avoid maximally fitting the training data only, right? So eventually or empirically it gives the better accuracy on the unseen data, right? So that is the main idea of the regularization, right? So the lower part is working exactly in the same manner. So here our main purpose is still distinguishing or classifying male or female given a person's image, right? So this lower part of our objective function or objective term is not our it's not our goal, right? So by combining these upper part and the lower part of 1 and 2 in this manner, okay, so this is our objective function. So we are not we are not optimize the first term, but we have to care about this second term to minimize that as well, right? But eventually, once we apply the model trained that minimizes both of these terms in that combined form, okay, so that will work better for the unseen data, right? It works as a kind of regularization kind of effect. And the main kind of plausible reason or reasonable explanation about why this kind of thing works as a kind of regularizer that improves the test data performances is because so once we suppose our training data had all the female person's images as having kind of longer hairs, okay? So again, our training data has all the female images as those having the longer hairs. And then if you remember kind of dropouts and those kind of regularization stuffs, and then our model will be easily prone to getting overfitted by just focusing on the hair part, right? So again, our training data has the like female images all having the longer hairs, long hairs, and then our model will be trained by just focusing or by only looking at this long hairs, right? But what if our test data has the woman's images that has short hairs? So in that case, our model trained by using this limited training data will not perform or will not generalize well for those unseen data, because that has these unseen patterns, right? But in this case of, so this lower part is called the autoencoder because it actually encodes some images into some activation map, but it has to be converted back into these original image, right? So that way it is called the autoencoder because this auto means it's not like automatic, but it's it has the meaning of the self, right? So it's like self-encoder, right? So if you know the term of autography, what is the meaning of an autography? In Korean, autography means 자서전이죠. 자서전. 그러니까 남이 내 뭔가 인생을 써주는 게 아니라 내가 내 인생을 쓰는 게 자서전이잖아요. 거기서 이제 오로가 자기가 썼다 해갖고 그게 오로거든요. 네, 그래서 이 오토 인코더는 뭔가 자동으로 인코딩을 해주는 게 아니라 자기 자신을 인코드하는 거라고 해서 오토 인코더예요. Okay, so the lower part is called the autoencoder. So if we add this autoencoder part as our part of our multitask learning framework for our kind of own task, whether it is a gender classifier or maybe age classifier or facial expression classifier, okay, so we have our own kind of goal or task, but this kind of autoencoder works as kind of is added as a regularizer to our module, and then this part, okay, this encoder part should actually satisfy this gender classification task and also this autoencoding task, right? And so if you imagine this autoencoder part, how can we perform well on this autoencoder task, right? So if our network, if our task is just to discriminate or classify the genders, and then it will be kind of easy because we can just focus on a specific kind of part out of the entire image. So it will not properly learn about the various kind of characteristics of our face, right? So our face has a lot of different kind of semantic meanings. Whether a person has a small eyes or large eyes, or maybe and skin tones and so on, right? So all the different components existing in our to represent our facial images, among them our task may require only a specific part, right? So but on the other hand, in the case of this autoencoder part, in order to reconstruct for each image, we want to reconstruct it into the original kind of images, and then we should be able to learn, or we should be able to remember all the different characteristics of our images. So that way, this part is not enough to just focus on or just to remember or encode like a hair part. Okay, so in order to reconstruct the original images, it has to remember or encode all the various semantic informations available in our facial images. So that way it can encode some some semantics of skin tones, or maybe shape of an eyes, and so on. So all the different information is encoded in this part, and thus it will help to perform our main tasks much better for unseen data as well. For example, even for those unseen patterns of female images having short hairs and so on. So does it make sense? Any questions? So yeah, this autoencoder, I mean, we will study this autoencoder, and it's a more advanced version called the variational autoencoder in a later lectures. So yeah, and also this autoencoder is quite widely used. So yeah, it's quite important part. Any questions so far? Okay, so we touched or discussed about really important concept of multitask learning, right? And also this autoencoder part. So it is a quite important part to remember. And let me discuss briefly, hopefully, about this ResNet. So one question was about the main intuition of this ResNet. Okay. So in this case, the main point of this figure is that we stacked more layers from 20 to 56, and then for this test data, even if we used much complex model that has more layers, and then it may happen, it may quite happen for the test data, it works worse than the lower layer model, right? So it's a more complex one, and it's a simpler one, and sometimes complex ones works worse than the simpler ones for the test data, right? And that is because overfitting. That is because of the overfitting, right? But in this case of a training error or training data performances, it actually doesn't make sense at all, because if we used more complex model, and then in general we have more number of parameters involved in our model, and then we have so we should have a better performance by using a more complex model than the case using a simpler model, right? So at least in the case of training errors, this complex model should be below this simpler model's performances, right? But people actually tried this complex model by stacking more and more layers, but they found this weird or strange phenomenon. Okay, so people thought about why it should happen that way, right? And so in general, it can be viewed. It could be due to the limitation of our imperfect gradient descent algorithm. So gradient descent algorithm, when using it to train a more complex neural net architectures, and then it might be prone to worse local minima compared to this simpler models, right? So that might be one kind of explanation. But anyways, in practice, when using this complex model, and then it works worse, than the simple model, even for training data. So it didn't make sense at all. So so in order to overcome this issue, people actually this guy Kai-Ming He invented this residual network, and then his hypothesis is as follows. suppose we have maybe 20 layer neural net, okay? And then suppose we added one more layers, okay? And then if this 21 layer performs just as good as this 20 layer model, and then yeah, this part should work just as an identity mapping, right? So in that case, this 21 layer model will work exactly the same as 20 layer model, right? But yeah, that is actually difficult to obtain, okay? So that is his hypothesis. And how can we achieve the identity mapping in this layer? So again, the situation is that, okay, 20 layer is just enough number of layer for our own task. And then if we use more layers added at the end, and then if that added layer works as an identity mapping, and then yeah, it should just work as the same as the 20 layer model. So in that case, identity, how can we achieve this identity mapping? So for example, suppose this additional layer is having 3 input node and 3 output node. And then what will be our identity mapping? Yep, our identity mapping will be like, so this guy is 1 for this direction, and also this guy is 1, and this guy is 1, and also this and this, yeah, should be set as 0, right? So among many parameters, some ones should be set as 1 or trained as a value of 1, and then some other, I mean the rest of them after, except for these selective ones, should be learned as 0, right? So that's how we achieve this identity mapping, right? Or in this case, if we have an input vector and output vector in this form, and then y is also y and x are both 3-dimensional vectors, and then yeah, our input vector x, and then this identity matrix should have this form, right? So 3 of them should be 1, and the rest of them should be 0. And so, I mean, among many different parameters that we need to optimize or train during our gradient descent, and then achieving this simple, I mean, although conceptually it is simple, yeah, it is sometimes difficult to find that, this kind of values as our final or optimal kind of local minima or optimal point through our gradient descent iteration, right? Okay, so that way, yeah, he just or Kaiming actually changed this structure in a way that, you guys know the rest of the stories. So we are adding it to the output, right? And then in this case, if we just need the identity mapping on the additional layer that we actually we added at the end, and then this matrix should just be enough to just produce, I mean, it would be just okay to just learn those parameters all as the zeros, right? So in this case, if we add the original vectors, and then by just simply learning or finding out all the optimal parameters as zeros, and then there is no no issues of selectively optimize some parameters as 1 and then the others as zeros. Okay, so training kind of this kind of pattern is much easier, and so that is the main idea of this ResNet stuff. Okay. And then also in terms of this gradient flow, I mean, through the backpropagation, the dy arrived at this point, and then it actually has, this guy is these 2 branches, right? So 2 branches, and thus gradient will also flow through this direction and this direction. And then in this case, if this part was not trained properly, And then, yeah, this part will be multiplied with the dy to produce the gradient with respect to this dx, right? So in that case, if this part was not properly trained, and then the gradient through this layer will also be kind of, yeah, a little bit kind of garbage kind of information. So yeah, so this is not trained at all, and then gradient will not be reliable. Okay, so in that case, this gradient is just backpropagated with an untouched state, or without any kind of distortion. It is just a backpropagated to this input variable. Okay, so that is also another kind of advantage of this ResNet. Yeah, and let me add one last remark on this ResNet. So in this ResNet, input and output activation map, if it is a fully connected layers, and then I just gave the example of having a fully connected layer having with the same input and output activation maps, size in terms of a size. So what if we have different activation size between input and output? In this case, can we apply this ResNet or this skit connection? So it is not, because we have a 3-dimensional vector, and then in terms of an output, it has 2-dimensional vector, so we cannot add them together. So in the case of, when applying the ResNet, it is impossible. So input and output should have the exact same size of an activation map. So in the case of convolutional nets, for this conv layer, so it should maintain the same spatial resolutions as well as the same number of channels between input and output. That way, that's how we can add those two tensors into one tensor. Okay, so that's one limitation, or that's one kind of important characteristic. But in the case of a dense net that we studied in the later slides, and then it is just works as a kind of concatenation between these two input and output activation maps. So in this case, the activation map size can be different. Okay, so the time's already up. So that's it for today. And so then this Wednesday, so you don't need to watch any more videos. Okay, and then we will continue this RNN and the attention models in the next lecture. Thank you.